So we learned that linear approximations are only accurate really close to the tangent that is used to approximate that function. So now we're going to introduce another method of approximation referred to as the Taylor's series or the Taylor's polynomial, and brought to you by the Taylor's theorem. Now, Taylor's is another approximation method. It utilizes the power series. It's a special case of the power series, but we'll discuss this in more detail as we go about introducing the idea of it using the most simplified forms of what is available for Taylor's theorem. And the gist of it is basically that given certain conditions, you can approximate or represent a function using the Taylor's series. And again, the Taylor's series is a special case or special form of the power series, which is why we're going to begin our discussion with the power series. So the power series is essentially just the infinite sum of the form you have a0 plus a1x minus c plus a2x minus c squared plus a3x minus c cubed plus a4x minus c to the fourth plus, and it goes on. So it's that infinite sum situation. So you have your function is equal to your summation, where n is equal to 0 to infinity of a to the n x minus c to the power of n. So it's an infinite series of this form. So this is your power series. Now we are going to simplify this before we continue discussing, particularly regarding the Taylor's series. So we're going to simplify it by firstly saying, hey, let's actually make c equal to 0. Okay, so now we have the form a0 plus a1x plus a2x squared plus a cubed x cubed plus a4 x to the 4 plus, and continue on. Now, this should make it a little bit easier to see that it's representing, a polynomial. And if you look at just the first one, that's just a constant because those a's are constant coefficients. And then you have the second version, which is a0 plus a1x. That's like your straight line. It's your linear. And if you look at, the next round, a1x plus a2x squared, that's your quadratic function occurring. And if you go a little bit further, you have a1x plus a2x squared plus a3x cubed, and that is your cubic. So this power series is giving you this polynomial kind of a representation for whatever function you have. And obviously you'll go up higher in the number of, or in the order of your polynomial, dependent on, what your function looks like. So how high you go is it's going to give you a more accurate representation of certain functions. But we are going to now look at this. So this is going to approximate our function, right? Now, if we want this to approximate our function, we kind of need to know what those coefficients of a are, because otherwise it's unknown. How's that going to help us? So we need to look at a way for determining those coefficients of a. So when we do this, we're going to once again make it even easier for us to do. So again, we're sticking to the most basic versions of this. It can get more complicated. We stick into the basics. And we're going to be like, okay, fine. We have a function. This is your f of x is equal to this. And we are going to look at the case where the x, let's choose a different color here. The x is equal to 0. So now if x is equal to 0, let's put it in. So then we have f0 is equal to a0 plus a10 plus a20 squared plus etc. And we look at that, this one cancels out, this one cancels out because it's all zeros. So we're left with a0 is equal to f0. So hey, we have one of the coefficients now. We know that given the situation, our a0 is equal to our f0. And we can continue this. So let's try solving for A1. And at this moment in time, you may be thinking, well, I can't go any further because it's A1 times that x, and that x is equal to 0, so that cancels it out. So now we're going to have to think about, okay, how do we get rid of that x that is next to that A1 so that we can do something very similar to what we just did over here? Hopefully you're like, wait, what if we take the first derivative? Because if we take the first derivative, that x disappears. So we have a case of, okay, the first derivative of that function is equal to a1 plus a2x plus a3x squared plus a4x to the cubed, etc. And now we can be like, okay, we'll take the first derivative at 0, and then we have a1 plus a2 times 0, and all the rest is 0, so we don't have to stress about it. So now we have that a1 is equal to the first derivative of 0. You're like, well, that was not that bad overall. We now know what a0 is, and we know what a1 is. Now, can we determine what a2 is? Now, at this moment in time, you may be going, oh, well, a2 is just the second derivative at 0. You're leaving out some math. So we're actually going to go ahead and do it first. So it is the same process. You're going to take the second derivative and then solve for it from that point. But just be very, very careful now, because there is an aspect involved here. And I actually did the math wrong, yeah. Oof. What math did I do wrong here? I didn't do my derivative correctly. This was 2a2. This was 3a3. That was 4a4. Why? Because if you take the derivative, remember this comes to the front. So just be very careful about that. I did the very thing that I was wanting to discuss as the most common mistake. So now we need to go ahead and take the second derivative. So let's first write the function f of x is equal to a0 plus a1x plus a2x squared plus a3x cubed plus a4x to the 4 plus and dot, dot, dot. Let's take the first derivative. That is a0 plus a1x. And that x goes away, remember, because it goes to the front there. That a0 goes away as well. So we have a1 plus 2a2x plus 3a3x squared plus 4a4x cubed plus, and continue on. Then we take the second derivative. So that a1 goes away. We have 2a2 plus 3 times 2a3x plus 4 times 3a4x squared plus dot, dot, dot. So now when we want to solve for, our a2, we're going to look at the second derivative equal to 0 is equal to 2a2 plus, and then all of these are going to be 0. So we get left with our second derivative at 0 is equal to 2a2, which means our a2 is equal to our second derivative at 0 divided by 2. Now we need to solve for our third derivative, our third a. So we need our third derivative. So we have the third derivative is equal to, and we have 3 times 2 times 1a3 plus 4 times 3 times 2a4x plus, and continues on. Then we say, okay, well, that third derivative equal to 0 gives you 3 times 2 times 1, and that a3 is just chilling like that, plus, this 4, 3, 2, a 4, 0. And that's going to, cancel out because it's 0. So we now have that a3 is equal to that third derivative divided by 3 times 2 times 1. And now you can slowly start seeing that there's a pattern forming regarding these coefficients of the x's, the a's. So the pattern is connected to what's happening over here. So what's happening over here is as you're doing your derivatives, you start off with the number, obviously, that original x was to the power of, and then it goes down all the way. So it has like 4 times 3 times 2. And if you had the fifth one, it would be 5 times 4 times 3 times 2 times 1. And that is the factorial. So we have a pattern occurring that f to the n of 0 is equal to the n factorial, the a to the n, which gives us that the a to the n is the nth derivative divided by the n factorial. So that's where we get our generalized coefficients of n from. So you can go and practice it. You can go and take the fourth derivative and the fifth derivative to confirm that this is in fact the case. But what happens is, in this situation, if we look at, this case where our c is equal to 0, and then we start solving for our x is equal to 0 kind of situation, we get our a coefficients as this value over here. And that means we can rewrite that series with the a written in. So we don't have the a's unknown anymore. We have it as a known value based on the function, derivatives of the function. So let's just write that out. Okay, so we're going to take that a, n is equal to, fn 0 n factorial, and we're now going to use it in that function. So we have f of x was equal to, and it was a summation of n is equal to 0 to infinity of a n x to the n. And we're going to now replace that a n with what we had worked it out to be, all those a coefficients to be. So it's n is equal to 0 to infinity of f to the n at 0, n factorial x to the n. And this is a special case of the Taylor series referred to as the Maclaurin series. All right, so it's a case where you take the approximation around x equal to 0, or about x equal to 0. Now what we can do is we can extend or go back to that case where c is not equal to 0, so we're not taking it about 0. And all that's going to do, it's just going to bump up our equation a bit more, and is going to result in our equation looking something like this instead. So our function is equal to the summation n is equal to 0 to infinity fn c, what we're taking it around, n factorial x minus c to the power of n. And this is going to be our Taylor series. Okay, so this is the special case about x equal to 0. And then our Taylor series is the more general case where we have a c, we can put in any c value where we're going to approximate around. And that f of x is the same as when we did the linear approximation, we said L of x is equal to, and we had f of a plus f prime of a x minus a, and that was the approximate value. So that f of x is that approximate value of the function now. So let's just go ahead and rediscuss that. So we have the Maclaurin series, and that's about x equal to 0. Then we have Taylor series, and essentially where the 0 was, there's now a c. So it's chilling over there, and it's chilling over there. And again, it just gives you, that long formula. And then we have, so that's the series, and the series is an infinite series. Now we have a thing called Taylor's polynomial, which cuts it, stops it at a point. So instead of having n is equal to 0 to infinity, we are going to have I is equal to 0 to n, where n is the order of the polynomial. Okay. And then we say, oh, we want the fourth ordered Taylor's polynomial. We'll just sub in n is equal to 4, and it's going to have a stopping point to it. So it's only going to go up to that x to the power of 4 kind of situation. So Taylor's polynomial is a very set, it has an order, it's first, second, third, fourth, fifth, sixth, 27th, whatever. But it does have a stopping point, whereas Taylor's series is infinite. Obviously, we can't work out Taylor's series because it's infinite, but we can work out Taylor's polynomial. And what we'll have to consider then is, obviously, because it's not infinite, it's not going to give us the most accurate of the approximations. So we will have to discuss the error that is produced by approximating our function with Taylor's polynomial. But right now, we have the Maclaurin series, which is where about x equal to 0. We did how we get those values with the Maclaurin series because I think keeping it simple makes it a lot easier for you. We then have Taylor's series where we generalize it, so we no longer have it about x is equal to 0, and you're welcome to go ahead and do the working out again to confirm that I'm not lying. Then we have Taylor's polynomial, and Taylor's polynomial takes just a section of the infinite series, which is Taylor's series.